Good day, everyone. And we're making a video today specifically with regards to number bases. So, the first thing we're going to do is look at where our system that we're using comes from. It is the Hindu-Arabic numeration system. And we look at some specificities of that. The first of which is the place value concept. And they, as we're using it, know that we have a place value concept. And this is different to some of the numeration systems before. And if we look at this general idea of how it developed, from early on, we could see 1, 2, 3 in the Brahmi first century, 4, 5, 6, 7, 8, 9. And there were only 9 symbols. And it developed later on in the 9th century to include a little circle or a dot at the end to represent our 0. Until by the time we reach the bottom one, which is what we're using now, it has all of those. So what it says is that apart from having a place value concept, it also includes the number 0, not just as a place value holder. And this is different to some of the numeration systems in other areas. And that means that if it has a 0, then we're counting from 0 to 9, which is 10 digits. And we're well aware that we count in base 10, which is also known as the decimal ordinary system. And look at an example here that we're accustomed to. We have ones and we multiply by 10 to get tens, and we multiply by 10 to get hundreds, and so on and so forth. And if we're going to the right, we'd be dividing by 10. And if we're smaller than a whole, then we have decimal point, which carries us to the point of tenths and hundreds and thousands and so forth. And let's look at this number, 2034. Just as a quick reminder that the place value of the number 3 in this particular number is 3 tens. That's the value of that column. And of course, the value of 3 will be 3 tens are 30. That is how much it's worth. So now let's get into our bases. And there are many bases that we can look at. So we look at the base 3. So we can consider 1 cube as a unit. And if we're using base 3, then we're moving to the next place value by saying 3 groups of 1. And of course, 3 groups of 1, if we're using blocks that can connect to unifix cubes or so forth, then that can be represented as a group of 3. Because it's base 3, and when moving to the next place value, then we'd have 3 groups of 3. Just how we had 1, and then 3 groups of 1, we now have 3 and 3 groups of 3, which is 9. And if we want to go to the next set, we'd have 3 groups of 9, 1 group of 9, 2 groups of 9, 3 groups of 9, which will be 27. And if we had to go again, we're limited by space, then we'd have 3 groups of 27. 27 plus 27 plus 27, which is 81. And for visual representation, we can rearrange this 9, remove 1 group of 3, and then the next group of 3, and what we actually have is something that looks like a square, right? That front face. So that could be considered 3 squared, which is 9. And just how we rearrange in 9, we can rearrange the 27. So let's remove a group of 9, put it at the back, and another group of 9. And what does this show us? That 27 can be represented as a cube, as 3 cubed. So let's bring up a little table so we can identify that. Let's start with the 3. We have 1 group of 3, so 3 to the power 1. In 9, we have 3 times 3, so that's 3 squared. And 27, we have 3 times 3 times 3, or 3 cubed, and so forth. And if we wanted 81, 3 to the power 4. Since math is patterns, it means that if we look at the powers there, then it'll be 3 to the power 3, 3 to the power 2, 3 to the power 1, and then what would 1 be? 3 to the power 0, Remember, anything to the power 0 is 1. So let's consider that we want to look at this particular number and identify it in base 3. Then what do we have? Let's bring up some spaces here so we can identify it. Remember that how many groups do we have in each place value? So let's start with the ones. We have 1, 2 of them. So let's bring that up. How many groups of 3 do we have? We have 0. And remember, we're still operating in the Hindu Arabic numerical system. So 0 is present. That's the system we're operating in. And how many groups of 9 do we have? We have 1 group of 9 or 1 group of 3 squared. And how many cubes do we have? We have 2 groups of 3 cubes. As such, we recognize that the digits that are possible are 0, 1, and 2. Could we get the digits 3 written in any of those columns when we're dealing with base 3? Well, let's look at it. If we had 3 groups of 1, they would not stay there. They would form a group and move to the second place value into the groups of 3. If we had 3 groups of 3, that is 9. So physically, we cannot form 3 groups of 3 and stay within that column, because 3 groups of 3 would be 9 and we have to move to the next place value, and so on and so forth. 3 groups of 9 would mean 27. So we are not able to write the number 3 in any of those when we're dealing with base 3. In this system, you can either write 0, 1, or 2, which is 3 numbers in base 3. So let's recall that each digit's value is based on its place in the number. So that's why we have a place value system. So let's look at this number that we wrote there, 2102 to base 3. And if we're doing that, let's expand the values. We will have 2 by 3 cubed plus 1 by 3 squared, because we have 2 cubes, 1 square, 0 threes, and 2 groups of 1, and 2 groups of 3 cubed, 2 by 27, that's 54, and 1 9, and 0 threes, and 2 ones. So if we're actually counting how many unit cubes we have in all, that'll be 54 and 9, 63, and 2, 65. So this is 65. So what we're actually doing is being able to see, using expanded notation, how we move from base 3 to counting them up, which is actually 65 or 65 units, which really means 65 to base 10. Let's go look at another base doing the same thing so we get a better understanding of it. Let's look at base 4. And if we're going through the same route, well, we have 1 unit represented by 1 cube, and we're moving across to the next place value. So that means 4 of those. So we'll have 1, 2, 3, 4. So 4 units will now give us our next place value, and then we'll have 4 groups of 4, and of course 4 groups of 4, we can arrange it as a square, which will give us 16, and then we can arrange 4 groups of 16, one behind the other, so it'll give us 4 by 4 by 4, which is a cube. So let's do the same, bring up a table and represent them accordingly. 4 to the power 1, 16 is 4 squared, as we can see a square there, and we can see 4 cubed, and if we went on, 4 to the power 4, 4 to the power 5, and so forth. And if we're going to the right, then units will be 4 to the power 0, because anything to the power 0 is 1. So the digits are 0, 1, 2, and 3, because we know that we cannot write 4 of any one individual column, because that actually carries us into the next column. So we are in base 4, and therefore we have 4 digits. So let's consider dealing with this number below. So we have 2 cubes, 3 columns of 4, and 1 unit of 4. So we want to be able to convert that eventually. This can be written as 1 unit, 3 groups of 4. How many squares do we have? How many groups of 16? 0. And how many cubes do we have? We have 2. So let's take a look at that as the idea of how it's written in base 4. It's 2031 to base 4, and in expanded notation, it will be 2 by 4 cubed because it represents 2 cubes, and 0 squares, and 3 columns, and 1 unit. And we could work that out. 4 cubed is 64, so 2 64s are 128, plus 0, 16s, plus 3 4s are 12, and 1 is 13. If we add that up, 128 and 12 is 140, and 1 is 141. So this actually tells us that if we separated it, we would have gotten 141 units, or 141 cubes. Right. So we've looked at base 3, we looked at base 4, and let's remind ourselves of the one that we're accustomed to, base 10. And we're going to represent it as 10 units there, 100 units, 1,000 units, and of course, 1 unit. Right? And let's bring up our table so we can say 10 to the power 1, 10 to the power 2, and 3, and of course 10 to the power 0, because we can see it's basically units, and then what we have is 10, a group of 10, which is called a flat or a rod. Then we have 10 squared, and then 10 cubed. We actually have physical representation of this for students to use called base 10 blocks. Now, let's record the digits that we use are from 0 to 9 in any one column. We cannot write 10, as we said before, in any column, because 10 units or 10 ones will actually give us one group of 10. So we'll have to move across to the next stage. Or 10 groups of 10 will give us the square, which is 100. So the biggest number we can write is not 10, but one less, which is 9. And if we count the digits from 0 up to 9, we have 5 and 5, 10 digits there. And 10 digits we can write because it's base 10. So let's try and represent this number here. And if we represent those numbers, we will have some cubes, some squares, some rods, and some units. So how many units do we have? And cubes, let's go. We have 1, 2, 3, 3 cubes. We have 1, 2, 3, 4, 4 squares. We have 1, 2, 3, 4, 5, 5 tens, and we have no units. So this means 3, 4, 5, 0 to base 10. And if you use expanded notation, it is 3 by 10 cubed plus 4 by 10 squared, because 4 squares, 5 flats or 5 rods, and 0. So that will be 3,000 plus 400 plus 50 plus 0, which means that if we separated out what was given down below into individual units, it will give us 3,450 individual units. Now, what does that tell us? That if we're looking at base 10, 3, 4, 5, 0 to base 10, which we have in blue, it actually means it's going to give us 3,450 units. So what we're saying is what we're accustomed to writing is what is in red there. And it means that base 10 is what we're dealing with. And it gives us the same value, so therefore it's understood. So any number we normally write in our operations is actually in base 10. Okay, so let's go now and see if we can look at some operations. So Sid collected 392 bottle covers. They said nothing else. So we assume it is in our normal base, which is base 10. So we have 3 hundreds. How many tens? 9 tens, 3 and 3, 6 and 3, 9, and 2 ones, or 2 units. So Sid collected this amount of bottle covers. So we're representing those bottle covers using these blocks. And he received another 1,646 covers. So that'll be 1 cube and 6 hundreds, 3 and 3 600s, or 6 squares, 4 tens, so we could bring that under the tens, and 6 units. What is the total? So total means we need to add it up. So let's set up the same system again. We're going to show the representation first of all, before we bring up the table, and identify, of course, we know ones, tens, hundreds, and thousands, which we're accustomed to adding with. So we're starting from what we know, base 10 to add, and then we do other other bases. So that's 10 to the power 0, 10 to the power 1, 10 squared, 10 cubed, accordingly. So it's really telling us 392, that's what we would be normally writing, plus 1646. So we're showing it with the bases so you can see what it's actually doing. And we're accustomed to this. What is happening? We're adding the units first. So if you look on the extreme right, we have 2 units up on top and 6 units below. If we put them together, we have 6 and 2, 8. And we could write that in. And now, if we're looking at the second column on the right, which is groups of 10, we had 9 first and we got 4 more. So we have 9 and 4, which gives us a total of 13 units. Now, 13 units really means that we have a group of 10 plus a group of 3. So we actually have 10 plus 3, please remember that, and we can't write more than 9, so we can take this 10 groups of 10 and replace it. And 10 groups of 10 will give us 100. So what are we left with? We're left with 3 groups of 10. So our normal working, you don't have to, but teachers recommend that you cross the 3 and write it in there now. And what we're left with is not 1, we're left with 10 groups of 10. And that has been replaced because it's base 10 by 100. So now if we're looking at the hundreds, we had 3 groups of 100 from Sid first collecting, 6 groups of 100 from what he received again. So that's 9. And we just replace the 10 groups of 10 by another 1. So we have 3 and 6, 9 and 1, 10. So this entire thing here is 10 groups of hundreds. And if we represent that there, that will be an entire block that we're showing. So we wrote 10 below, and how our algorithm will teach us will be 3 and 6, 9 and 1, 10. So we write that. And we can't write 10 in one column because it's up to base 10. So what do? 10 groups of 10 can be replaced by a group of 1,000. So 10 groups of hundreds, will be 1,000. As such, we need to write that in. So how many groups of hundreds do we have? No more. So we can cross it and put it in there. And how many cubes do we have? Groups of thousands. We had 1 and we got another 1. So that is 2. As such, our answer is 2038. So we're just trying to show the representation and showing what we call regrouping every time we have to carry it across. And it's not really, it happens to be 13, but it's really 10 plus 3. And the 10, because it's base 10, causes it to move to the next column. So let's go and let's look at another operation. Let's use base 3. Find the sum of 211 to base 3 plus 202 to base 3. So let's represent it as usual. Bring up the units, the groups of 3, 3 squared, 3 cubed. So that will give us 1, 3s, 9s, and 27s, or 3 to the power 0, 3 to the power 1, 3 to the power 2, 3 to the power 3. And this question can be written as 211, which is base 3, plus 202. And how do we do that? Well, we're supposed to, in our classrooms, be able to apply this by adding downwards, but I want to show a physical representation of it. So we have 2 groups of 9 and 1 group of 1 and 1 group of 3. So we have that from 211. Right? 2 groups of 9, 1 group of 3, 1 group of 1. And we're going to add that to 202, which is 2 groups of 9, no groups of 3, and 2 units. So we have 1, 2. Now, if we're adding, we want to start by the right-hand side in case we have to regroup. So if we consider on the right side our units, we have 1, 2, 3 units. And we know this is base 3. We cannot write a 3 in there. So 3 units can be replaced by 1 group of 3. So what that tells us that 1 and 2 is really 0 units and 1 group of 3. So it looks like it's 10, but what it really means is 0 groups of 1s and one group of 3, which is what happened here when we did the replacing or the regrouping. So now 1 plus 2, teachers tell us to cross it off and write it. You don't need to cross it, it's fine. And now that we've done that, we can see we have no units. We now count in groups of 3s. We had 1 initially, and with the regrouping, we got another 1. So we have 1 and 1. So that will give us 2. And that is allowed because in base 3, we are allowed up to the number 2, 0, 1, and 2. And now let's look at the groups of 9 or 3 squares. So in those squares, we have 1, 2, 3, 4. And we can see that from our algorithm, 2 plus 2 is 4. And the most we can write is 2. So can we look at the groups of 9 and we realize that we can group them together. 3 groups of 9 can be replaced, and I'll give you one group of 27 or a cube. So what is happening there? 2 plus 2 in groups of 9 is 4, which is really one group of 9 and one group of 27. So it may look like it's 11, but it's really one group of 3 squared and one group of 3 cubed. So we can now cross it and write it in there. And now if we have to add up all the cubes, we only have 1. So our answer is 1, 1, 2, 0 to base 3. And can we check if that's correct? We have 0 units, 2 groups of 3, 1 group of 9 or squared, and 1 group of cubed or 27. So it makes sense. So that's the way we can add and so forth. So let's now move on. We did that operation of addition. Right? Let's look at this idea here. Helen had $4,236. So if we're counting money, we assume it's in base 10. So 4 thousands, 2 hundreds, 3 tens, and 6 ones. She had that amount of money, so we represent it using our base 10 blocks. And of course, let's set up our table as usual. We have ones, tens, hundreds, thousands. And of course, that means 1, and we can write it as indices 10 to the power 0, 10 to the power 1, 2, and 3. And that is 4,236. Let's go on to the next part of the question. She bought a washing machine for $3,173 from that money. So that means how much money is left. This sort of question is the operation is subtraction. So it can be written like that. And we can do our normal subtraction or minusing for each column, and that's fine. We want to set it up so you could see it from the idea of the cubes. So we had 6 units. We start on the right-hand side, or the smallest one, in case regrouping is needed. And when we have 6 units, what do we want to do? We want to take out 3 units. If we look in the ones column in the table, you can see that. So if we have 6 units on your right, let's take out 3 of them and put them one side in this pink collection here. That will be our money we're going to take out for the washing machine. And whatever remains on top is what is left. So 6 minus 3 is 3. Now we have 3 groups of 10. And what do we want to subtract? For the washing machine, we want 7 groups of 10 to come out. We don't have 7 groups of 10 to take out from 3. That's too much. So what do we need? We need to take one group of 100 and then replace it to 10 groups of 10. So now that we have done that, we can see it represented in the algorithm by doing what? Recognizing that we had 2 squares or 2 sets of hundreds, and we replaced it. So that is why we recommended to cross the 2 and leave it as 1. And now remember that the 1 set of hundreds was replaced by 10 sets of tens. So it's better for the students if they remember that instead of writing 1 next to the 3 to make it 13, it is really 10 sets of 10 plus 3 sets of tens, which is a total of 13 tens. And we can see that in the diagram. If we count the tens, we have 10 and 3, 13 in all. And now what do? The question says that we need to remove 7 tens in order to pay for the washing machine. So if we do that, then we have 3 and 4, 7 being removed. So we have $73 put away for the washing machine already. And what we're left with is 3 and 3 sixths, 6 sets of tens. And now we're looking for $100 to be removed. And we have 1 square there, or 100. So if we remove that, 1 minus 1 will give us 0. So far, we considered $236 that we had, and we removed 173. You can see it below. 100, 7 tens, and 3 ones, and we're left with $63. Now the last part, let's deal with the thousands. And with regards to thousands, we have 4 thousands, and we need to remove 3,000 to pay for the washing machine. So let's do that. So we're left with 1,000. As such, 4,236 minus 3,173 is 1,063. And we can see we're left with 1 cube, which is 1,000, 6 tens, 60, and 3 units, 3. So 1,063. And I know we normally cancel it, but we can see the collection that we removed was 1, 2, 3 cubes. That's 3,173. 7 tens and 3 ones. So it makes sense. Let's go on now to practice subtraction operation again, but we're going to do it with a different base. So find the difference between 1 to 1 to the base 3 and 1 to 1. So let's do the normal thing. Let's bring it up and recognize we have 2 units and then 1 group of 3 and then 2 groups of 9 and 1 cube. And this represents 1, 2, 1, 2. And of course, you can bring up our table with the normal representations. Those are for you to get a better grasp of what's happening. And we know the values are 1, 3, 9, and 27, or the indices version, 3 to the power 0, 3 to the power 1, 3 to the 2, 3 to the 3, because we're dealing in base 3. And we have 1, 2, 1, 2, which is what is represented there. And we want to find the difference. So we want to subtract 1 to 1. Now, can we deal with that? Let's bring it up like similar to what we did before, so we can see when we're removing it, where it goes, and check that back at the end to make sure we did remove the correct amount. So from 1 to 1 to base 3, we first of all want to start on the right-hand side in the units column. And how many units do we want to remove from those 2 that we have? We want to remove 1 unit. So we can do that. And 2 minus 1 is 1. So we had 2 units, we removed 1 unit, we left with 1. Good. For the next step now, we have 1 group of 3 presently, and we would like to remove 2 groups of 3. And we can see that from our algorithm. So we don't have enough groups of 3 to remove. So what do? We look at the next stage, and we have a group of 9. And that group of 9 can be replaced, and we've formed 3 groups of 3. So now, how is that represented? We cross 2 groups of 9 and write 1. And what else? We're adding 3 groups of 3. That's why it's better, instead of writing 1 there, we should be writing 3 groups of 3 plus 1 group of 3 is a total of 4 groups of 3. So now that we have 4 groups of 3, we have to subtract 2 from there. So let's take out 2, and that means we're left with 2 up on top. So we've done the units and we've done the groups of 3s. Let's now go do the groups of 9. We had 2 groups of 9, but we regrouped it, and now we're left with 1 group. So 1 group of 9, I'm going to subtract 1 group of 9, so we're left with 0 groups of 9. And finally, we had 1 cube, and we don't have to take away anything from it, so we're left with 1. As such, we started with 1, 2, 1, 2, and we removed 1, 2, 1. And we can see down below 1 group of 9, 2 groups of 3, and 1 group of 1. And we're left with 1 cube, 0 nines, 2 3s, and 1 1. So it makes sense. And let's look at a conversion of pieces. When I just remind you of those. So imagine we have 3 1 5 to base 8. So that can be represented as 5 units. 1 2 3 4 5, and we're considering base 8. So that's 5 units, and then one group of 8. So we can bring that up. And then 3 groups of 8 squared. So one group of 8 squared, 8 by 8, you can count it, 8 by 8, 8 by 8. And if we want to convert that to base 10, this can also be written as 3 8 squareds plus 1, 8 to the power 1, and 5 by 8 to the power 0. So considering that we want to move it to the point of base 10s, then we want to get squares of 10. So how do we do that? Let's look at this first group here of 8, and we're going to redistribute it. So we're going to take one of these and put it across. So that first square on the left-hand side, which was a 8 by 8, is now 8 by 9. And if we move another one, it becomes 8 by 10. So we're getting closer towards a 10 by 10 square. And why do we want a 10 by 10 square? Because we're moving from base 8, we're converting to base 10. And we can move up on top. So we have there, it's now almost 9 high. And we're getting to the point where we're 10 in terms of height and 10 in terms of width. Not quite a 10 by 10 as yet. And you could do the same with the second one, as all we're doing is grouping the form. So we're trying to get a height of 10. So we move those across. So it's a height of 10, but a width of 8. And we can move these closer. So width of 9, width of 10. So we're almost to the point of getting 10 by 10 squares. Now, where are you going to get these 4 and 4, 8 that's missing? Well, we could split up this group of 8 into 8 units. 1, 2, 3, 4, 5, 6, 7, 8. And we can take them and carry them across because we physically want to be able to fill that so that we get a 10 by 10 square. So we have one 10 by 10 square, and then we're now doing a second one. So what do we have in all? We have one 10 by 10 square, or 100, and a second 10 by 10 squared, that's 200s, and 5 units. So that can be represented as 205 to base 10. Or teachers ask us, the other way we can do it is just expand, right, using that notation we have. So 8 squared is 64, so 3 by 8 is 192. One group of 8 is 8, and 5 units are 5. So 192 plus 8 is 200, plus 5 is 205. So that might be the standard algorithm that's done in class, the way we move from base 8 to base 10. But what we're trying to do is show you conceptually what is happening is we're moving from 8 squares and 8 cubes and 8 units and groups of 8 to groups of 10 or 10 squared and so forth. So hopefully you see 2 hundreds, no 10s, and 5 ones. What about if we wanted to go in the other direction? In the other direction, we could do the same thing and regroup it just as we started and move them apart, put the greens and the oranges back together to form another group. So we'll have 1, 2, 3 groups of 8 squared, and then all the 4 and 4, 8 single units up in the corners can come together and form a group of 8. And we'll get 315. Or there are different ways to solve every math question. So we can think about it. If we want to move from base 10 to base 8, how do we consider that? Base 8 would be in units, 8s, 8 squareds, which is 64, 8 cubes, 512, and so forth, right? 4096 and going on. 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3. And let's see how many can we get, like 64s into 205, or 8s into 205, or so forth. Can we get groups of 512 and 205? No, it's too big. Can we get groups of 64 into 205? Yes, we can. So, how many 64s can we get into 205? A simple division, and it will give us 3 groups of 64, which is 192. We have that on the left-hand side. We can see it in our third line. 3 groups of 64 is 192, and we'll have a remainder of 13. And then, if we have 13 units, can we get a group of 8 in it? Yes, we can get one group of 8, and we'll have a remainder of 5. And then, if we have 5 units remaining, how many units is that? 5. So 205 to base 10 is really 3, 8 squareds, and 1, 8, group of 8, and 5 units, or 315 to base 8. And that's the conversion. Another version, which is very algorithmic, is really recognizing that we're dividing by 8s all the time. So 8 into 205 is 25, remainder 5, because that's 200. 8 into 25, if we do that division, it's going to give us 3. So what we really did is divide 8 8s are 64 into 205 and got 3. And our remainder is one group of 8, which is 8 and 5, 13 right now. And can we divide 8 into 3? You're going to get 0 and a remainder of 3. As such, our answer is 315 to base 8. So either method will work. So thank you very much for following the number bases explanation for notes for those students who are struggling.